Welcome back to the deep dive. So today we are tackling a bit of a ghost story.
A ghost story. In manufacturing.
You know the one? I think every machinist, every engineer has lived this. You're chasing that micron level precision. Your G code is perfect. Tooling is brand new. You hit go, and the machine just fights you.
Ah, yes. The ghost in the machine. I know it well.
Exactly. You get these chatter marks you can't explain,
Hmm.
or dimensions are drifting by the afternoon, even though you haven't touched a thing. It feels like there's a gremlin somewhere.
And that's usually when people start blaming the CAM software or the operator or, the coolant mix.
Right. But for today's deep dive, we're looking at what happens when you realize the problem isn't the software, it's the very skeleton of the machine.
Yeah.
We're talking about the foundation of modern CNC machining, mineral casting.
This is such a fascinating topic because it challenges that old school mentality. For what? A century, the rule was simple: heavy iron. If you want a serious machine, you pour iron.
But that's changing. We are unpacking a stack of research today that suggests the solution to the next generation of precision isn't some, I don't know, futuristic alloy. It's dirt.
Highly engineered dirt, to be fair.
Fair point.
Yeah.
Rocks and glue. But the data here it's wild. We're talking about a material that is 6 to 10 times better at killing vibration than cast iron.
Which is a staggering number.
So our mission today is to figure out why the industry is moving this way, how it actually works, and why mixing, nature with chemistry might be the only way to hit those tolerances we need for aerospace or semiconductor manufacturing.
It's really a story about physics versus tradition and overcoming that. It's just concrete bias.
Let's start right there, the perception problem. Because when I first saw mineral casting, my brain immediately went to, a guy with a wheelbarrow mixing quickcrete for a patio.
That's the biggest hurdle. You say concrete to a traditional machinist, someone who spent 30 years on an old Bridgeport, and they just recoil. They think of something brittle, cheap, porous.
So what's the actual recipe? If we're building one of these bases, what goes in the bowl?
It's a really highly engineered composite. You start with aggregates. That's your filler. So we're talking about quartz sand, granite chips, sometimes basalt. These are extremely hard minerals.
Okay.
But the key insight from the research is that it's not just a bucket of gravel. The size distribution of those particles is it's mathematically calculated.
Why does the size matter so much? I mean, a rock's a rock, right?
No, when you want density. Imagine you fill a jar with golf balls. You have all that air between them.
Sure.
Now, you pour in marbles to fill those gaps, then sand to fill the gaps between the marbles. You're trying to eliminate every possible void.
Okay, I see. Maximum packing density, you're trying to get rid of all the air?
Exactly. You want as little empty space as possible. And then you need something to hold that puzzle together.
Binder. The glue.
Right. And this is usually a high-quality resin. Which brings us to the menu, because the sources are clear that not all mineral casting is the same. There are really 3 tiers you need to know about.
Okay, let's walk through them. If I'm buying a top-of-the-line 5-axis German machine, the kind that costs more than my house, what is that base made of?
That would be the gold standard. Epoxy resin composite. This is where they mix those specific quartz or granite particles with a very high-performance epoxy system.
Why epoxy? What makes it so special?
It's all about the bond strength and stiffness. The epoxy creates this cross-linked polymer chain that gives you just incredible compressive strength. We're talking up to 160 newtons per square millimeter. It's also extremely resistant to chemicals.
So coolants, oils, that kind of thing.
All of it. It just shrugs it off. So that's the luxury option.
And what if I'm not making a surgical implant? What if I just need a base for some, light automation?
Then you might see the second type, polymer-based casting, which uses polyester resin.
Polyester like.
A leisure suit.
Amicably related, yeah. It's a cheaper resin system. It's easier to process because it flows a little better, but the trade-off is heat resistance.
It gets soft. It gets softer at lower temperatures than epoxy does, and it shrinks more as it cures. So for general purpose stuff, it's fine. But you wouldn't build a high-speed spindle housing out of it. It would just move too much.
Got it. And then there's a third type, which sounds more like a clever construction hack, composite mineral casting.
This one is my favorite because it solves such a practical problem. Imagine you have this giant, hard block of epoxy and granite. How do you attach a linear rail to it?
You can't just tap a thread into a piece of quartz.
You'd destroy the tap instantly. And even if you could, the rock would make for a brittle thread. You torque a bolt down, and you risk cracking the whole thing.
So what's the composite solution?
It's a hybrid. They take precision steel inserts, threaded blocks, rail mounts, bearing surfaces, and they place them in the mold before they pour the mix.
So the steel is just sort of floating in the mold.
Suspended in these really exact positions.
Okay.
Then they pour the mineral casting around it. When it cures, the steel is permanently locked inside the stone body.
That's brilliant. So you get the durability of steel where you need to bolt things down,
Oh, yeah.
but the vibration damping of the rock for the main structure.
Best of both worlds. It balances performance with the reality that you still have to assemble a machine.
You mentioned vibration again, and I really want to dig into that. Reading the reports, this seems to be the killer app. The notes use this analogy of a bell, which I thought was perfect.
It's the best way to understand the physics. Imagine a machine bed made of gray cast iron. It's basically one giant continuous crystal structure. If you strike it with a hammer, what happens?
It rings like a big church bell.
Precisely. It sustains that tone. That ringing is resonance. Now think about a CNC machine. Your cutting tool is spinning at, what, 15,000 RPM? It's hitting the workpiece thwack, thwack, thwack thousands of times a minute.
That's the hammer.
That is the hammer. And if your machine bed is cast iron, it starts to ring, it vibrates. And that vibration doesn't just disappear, it travels right back up the column, down the spindle, into the tip of your tool.
And that's the chatter we were talking about.
That's chatter. The tool starts bouncing off the material instead of slicing it cleanly. You get a terrible surface finish, and your tool life just plummets.
Because it's being beaten to death.
It's experiencing constant micro-impacts. Now let's swap that iron bed for a mineral casting one. I hit it with a hammer. What happens?
Just a thud.
A dead thud. The vibration dies almost instantly.
But why? What's happening inside that material that just kills the energy?
It's the complex structure. In cast iron, the energy has a clean highway to travel on. In mineral casting, the energy has to go from a piece of granite through a layer of epoxy into a grain of sand back through epoxy.
So it's an obstacle course.
It's a maze. And every single time that vibration crosses a boundary between materials from rock to resin, it experiences internal friction. It loses a little bit of power.
And it turns into heat.
A tiny, tiny amount of heat. The energy just dissipates. The numbers on this were staggering. The damping ratio for mineral casting is listed at, what, 0.0241 to 0.044?
Which by itself is just a number. But compared to cast iron,
It is 6 to 10 times higher. We're not talking about a small improvement. We are talking about an order of magnitude difference.
so in the real world, what does that mean for an operator?
First, your surface finishes are beautiful right off the machine. Second, your tools last way longer, which saves a ton of money. But the third thing, which people really love, is the sound.
It's quieter.
Much quieter. The base absorbs the sound waves just like it absorbs vibration. We're talking a noise pressure drop of about 20%.
Wow. In a shop with 10 machines running, that's the difference between needing ear protection and actually being able to talk to someone.
It just changes the whole environment. It feels more solid, more controlled.
So vibration is solved. But there's another problem with metal that I hadn't really thought of. This idea that metal has a memory.
Oh, yeah. In precision engineering, that memory is an absolute nightmare.
It sounds like a bad romance novel. But what does it mean for a machine bed?
It goes back to how cast iron is made. You melt iron at, what, 1200 degrees Celsius, you pour it into a mold, then it has to cool down.
And things shrink when they cool. Basic physics.
They do. But a machine bed isn't a simple block. It has thick parts, thin ribs. They all cool at different rates. So as the metal solidifies, it locks in tension. We call it internal stress.
The metal is literally pulling on itself from the inside.
That is a perfect way to put it.
Yeah.
And over months or even years, the metal tries to relieve that stress. It relaxes.
And when it relaxes, it moves.
It warps. It works. It twists. You can spend a week getting a machine perfectly level, and 6 months later, the bed has curled up by 20 microns because the iron just decided to let go.
I've heard stories of old machine builders leaving castings out in a field for a year to season. Is that a real thing?
Absolutely. That used to be standard practice. You'd throw the castings out in the snow and sun and let the weather cycle the stress out over a year or two.
That's crazy in today's world.
It is. Nobody can afford to let inventory sit in a field for a year. So how does mineral casting get around this?
The cold cure,
The cold cure.
which means
It cures at room temperature, basically. The reaction between the resin and the hardener creates a little bit of heat, but the process usually stays below 45 degrees Celsius.
so no thermal shock.
Zero thermal shock. The shrinkage during curing is tiny, less than 0.2%. So once it sets, it is set. There's no internal stress. The shape you pull from the mold is the shape it will keep forever.
That geometric stability has to be a huge relief for anyone building a machine.
It's the foundation. You can't build a precise house on shifting sand. This gives you bedrock.
Okay, speaking of shifting, let's talk about the other big enemy on the shop floor, the one that causes the whole morning versus noon problem.
Heat, the invisible enemy of accuracy.
Well, walk me through. I come in at 7 a.m., my machine is cold, I'm running perfect parts. What's happened by loaf time?
Well, your spindle motor's been running for hours. That's making heat. The cutter is generating heat. Your hydraulics are hot. The whole environment warms up.
And cast iron is a conductor.
A great one. So
Yeah.
the machine bed absorbs all that energy and it expands. We call this accuracy drift. The machine is physically getting bigger,
So your spindle is now, what, 15 microns away from where it was this morning?
and you spend the rest of the day chasing tolerances, tweaking offsets. It's incredibly inefficient.
So how does the rack bed handle this? Does it just expand less?
That's part one. Yes, its thermal expansion coefficient is about 1/3 that of cast iron. So even if it gets hot, it moves less.
But there's more to it.
The more important factor is something called thermal inertia.
It's just thermally stubborn.
It is. Its thermal conductivity is incredibly low. We're talking less than 5% of cast iron.
Wow. So iron is like a copper wire for heat, and mineral casting is an oven mitt.
It's an insulator, a thermal buffer. It takes a huge amount of time for heat to penetrate the material. If the shop temperature spikes for an hour, the core of that bed barely even notices.
It acts like a flywheel for temperature, smoothing out the peaks.
Exactly. By the time the heat starts to soak in, the shift is over. It just holds the geometry constant all day.
I can see why this would be critical for 5-axis machines, where the geometry is so complex.
It's non-negotiable. In a 3-axis machine, maybe you just cut a little deeper. In 5-axis, if your center of rotation shifts because the bed warped from heat, all your calculations are garbage. The errors compound.
Okay, I have to play devil's advocate for a second. We've been praising this material, but there has to be a downside. What about stiffness? Iron is dense. Rocks are, well, lighter.
And that is the valid engineering counterpoint. Mineral casting has a density around 2.3 grams per cubic centimeter. Iron is about 7.2.
So it's a third the density. Doesn't that mean the mineral bed would be flimsy?
If you made it the exact same shape, yes. If you just copied a cast iron design, it would be a disaster. But you don't.
You change the design to compensate.
Exactly. Because the material is lighter, you can afford to use more of it. You make the walls 3 times thicker, or even better, you make sections solid.
Something you can't really do with iron.
Right. Pouring a solid block of iron is a metallurgical nightmare. You'd get voids and cracks. But with mineral casting, you can pour a massive solid block. So even though the material is less stiff, the final component, the machine bed, can be just as stiff or even stiffer than the iron one.
So you trade density for volume.
And by gaining volume, you get even more of that vibration damping we talked about earlier. It's a win-win as long as you design for the material.
It really does seem like the holy trinity for a machine base. You've got the vibration damping to kill chatter, you have geometric stability so it doesn't warp, and you've got thermal inertia to fight the heat.
It solves the 3 biggest physical problems that limit precision.
It makes you wonder why we stuck with iron for so long. Was it just tradition?
It was what we knew. We've been melting iron for thousands of years. The chemistry for high-strength epoxy is relatively new. And honestly, for a long time, iron was good enough.
When you're chasing thousandths of an inch, it's fine.
Right. But now we're chasing microns, submicrons. The speeds are higher, the accelerations are violent. We just reached a point where the iron itself was fighting the process. We needed something that would work with the physics, not against it.
It's a beautiful irony, don't you think?
How do you mean?
Well, you think about the path of engineering. We started with stone tools. We moved to bronze, then iron, then steel. We spent centuries perfecting how to cut metal with other harder metals.
Oh.
Now, the secret to the absolute cutting edge of technology, the machines that build our jet engines and our microchips, is to go back to the Stone Age.
Rocks and glue.
It's humbling. It makes you think that maybe the answer to our next big engineering problem isn't in some lab creating a new element. Maybe it's sitting right under our feet.
It certainly makes you look at a pile of gravel a little differently.
It does. Next time you see a granite countertop, just think, with a bit of epoxy, that could be building a part for a spaceship.
Or at least a very, very precise bracket.
That's all the time we have for today on the Deep Dive. Thanks for helping us dig into this.
It's a pleasure.
Keep it precise, everyone. We'll see you on the next one.